Right, so I guess we can get started. Okay, so all right, I'm going to kick off the seminar today. So good morning, everyone. My name is Sheng. I'm a postdoc working with NARA, and today I'm going to present our work on DiffTune and auto-tuning method using the auto-differentiation. So this will be the first half of the seminar today, and I believe Aditya is going to give the second half on the distributional robustness control. Which is very exciting. So, okay, getting back to DiffTune. So I would like to start my presentation by revisiting what are the missions we envision to be fulfilled by the advanced air mobility. So the vision of NASA is to help emerging aviation markets to safely develop the relevant technologies and systems so that in the near future, the public and the industry can benefit from AAM in various applications. For example, you can see here in the animations produced by NASA, there is emergency response, healthcare, cargo delivery, or air taxi. So to support so many applications and missions, the number of pilots we can train does not scale to the number of aircrafts that are deployed for the AAM missions. So these vehicles are going to be pilot-free or autonomous or intelligent, and we want these aircrafts to know how to fly themselves. So there are, for now, a number of questions or problems to be solved before this can happen. And one fundamental thing we need to design will be the controllers that can enable the AAM vehicles to fly these versatile maneuvers, say by tracking the planned trajectories to fly from point A to point B. These AAM vehicles have the vertical taking off and landing capabilities, which can be thought of as combining multi-rotor vehicles with fixed-wing aircrafts. So this forms a new drive for nonlinear controllers that can hopefully handle the complicated dynamics with these AAM vehicles. So towards this end, we have many methods for controller design for linear systems, for nonlinear systems, and eventually, to deliver the design performance, we need controller tuning. But tuning is often done by hand using trial and error, which is not efficient at all. And if you take a closer look at why this is hard by hand, there are two reasons. One is that the relationship between the parameters and the expected performance might very likely have a nonlinear relationship. That means you would need to have many trials to understand how that nonlinear relationship look like. And secondly, the dimension of tuning is a problem because the number of tuning decisions scale exponentially to the number of parameters. Say if you have for each parameter 3 options to take every time, you can tune it up, you can keep it as the same, or you can tune it down. And then suppose you have n number of parameters. Then in the worst case, every time you would do 3 to the power of n options or choices to decide which is the next set of parameters to go. So these are the two reasons what I think that can make tuning by hand very hard. So a solution that people commonly use to solve this problem is called auto-tuning. So people have built auto-tuning schemes which can be categorized into model-based or model-free. So model-based auto-tuning leverages the model knowledge to infer the parameter choice for performance improvement. And because the model is known, we already know how to guarantee stability of the system or say produce a certificate of the controller using maybe Lyapunov method or control barrier functions. But it is not easy to model for this model-based method to incorporate data that you possibly sample from a real system, because the model-based methods are generally based on simulations. And also it can lead to suboptimal tuning if your model has mismatched to the real system. And on the other end of the spectrum, there are the model-free auto-tuning methods, and they're often data-driven with readily available tools from the machine learning community, and they often make no assumptions on the system. But the issue is that they can have scalability issues as they can be inefficient when the dimension of parameters is high. So our question now is, can we combine the best of the two worlds? Combine the the knowledge of the models we know from the model-based approaches and then leverage the efficient tools from the model-free methods? Well, the answer is yes. And before showing our solution, which we call DiffTune, I would like to define the problem of controller tuning. So we consider a nonlinear discrete time dynamical system, and what you see here is an on-road form. It's just flattening this iterative dynamical system into this flat plane form. And we consider this feedback tracking controller. Here we're asking the controller to track this x hat that denotes the desired state, and we parameterize the controller by the parameter theta. So then the goal of tuning is to adjust the parameter theta to reduce the loss function on top. And the loss function can come from, for example, the evaluation metric of the system. One example I'm showing here is the tracking error. And there are also other metrics you can use. So mathematically, we formulate the tuning as a parameter optimization problem, where we look for the parameter theta to minimize this loss function subject to the dynamics and the chosen controller. So all we require here is that the dynamics and the controller are differentiable. And if you look at the literature in the recent years, because of the pushing from the machine learning community, many controllers are shown to be differentiable, like the explicitly differentiable PID controllers, or implicitly differentiable MPC, or optimal control, or control barrier function type of methods. So there are many controllers that are proved to be differentiable. So our method, DiffTune, applies to this controllers for tuning, and DiffTune is a gradient-based method. It has the nice features of stability, compatibility with real data, and efficiency. And I'm going to walk you through these features in the next couple of slides. So to see how DiffTune works, this is an overview of how we devise the method. So we start with the system, and we can collect the data that contains the state and control information within certain horizon, and we can evaluate the loss over this horizon. And then we proceed to compute the gradient of the loss function with respect to the parameter theta. And this is a very natural way to think about how you would decide your parameters by inferring about this first order information, the gradient of the loss function to parameter theta, to understand in which direction you need to change your parameters to reduce the loss function. But this cannot be trivially done because we know for control systems, the fundamental property we want is stability. And either from analytical perspective where you apply Lyapunov analysis, you would know that the controller will give you stability for the parameters within a certain range. Or empirically, if you're a control engineer, you work with controllers, then you know that some arbitrarily large or weird gains won't let the controller work. So there would be a feasible set of the parameters. Here we're denoting it by this capital theta. So maybe let me pull out the pointer. So this capital theta that describes the feasible set. And here, instead of doing vanilla gradient descent, we're doing projected gradient descent, such that the new parameters would always stay within this feasible set that obtained either through mathematical analysis or empirically designed. Okay, so with this, we get to the new parameter. So we put it back into the system, repeat this procedure, and then iteratively update the parameter until we can see satisfactory performance. So to give you an idea of how it works, on the right, I'm showing an animation of the auto-tuning for a quadrature tracking control. So what you see here is that this blue closed-loop trajectory using the parameters being updated every time is actually approaching this red desired trajectory. And then on the right, we're showing that the tracking error is monotonically reducing. We're using gradient descent, and this will iteratively give you improved performance. Okay. So the key of our approach here is actually to obtain the gradient of the loss function to parameter theta. So how do we do so? Well, conceptually, we borrow the concept of computational graph and auto-differentiation from the machine learning community. So what we do here is we look at this control system in this on-road perspective, where this can be treated as a computational graph conceptually. And when you have a computational graph, you would know that it is similar or conceptually same to a neural network where you can apply backward propagation to get the gradient. And then when you do so, when you try to do so, there are efficient tools for you to do backward propagation in simulations. And these tools are like PyTorch or TensorFlow that can do this backward propagation very efficiently. Quick analysis on backward propagation. I want to talk about the good and bad sides of backward propagation. So first of all, the good things are that there are already efficient tools, which makes really the implementation really efficient. And secondly, this gradient that we obtain using these tools, using backward propagation, is that this gradient will be analytical. And the benefit of analytical gradient is that it's not computed using approximations like finite difference, or using symbolic approach where it's the result is prone to errors when you code the program. So analytical gradient can give you better informed directions regarding which direction you should follow to change your parameters. So that's the good side. But if you know that next I'm going to talk about the bad side, I don't have much space left. Now this thing is really a bummer about backward propagation. The cause is that backward propagation is not compatible with the data that you collect from a physical system. Meaning that if you have a real system, you want to tune it with auto-tuning, and suppose you can collect the data, and now you want to get the gradient to know which direction you want to do the parameter change. Unfortunately, you cannot do it with backward propagation. And why is that true? Okay, so quick recap on how backward propagation works. So as the name suggests, backward propagation is a way that goes backward on this computational graph to obtain this gradient theta. But in doing so, it actually requires a forward pass first to know what the structure of the computational graph is, and then leverage the backward direction or backward propagation to do the computation for the gradient. So this forward pass indicates that whenever you get a new state, say xk, it is obtained exactly based on this computational graph where you evaluate the dynamics based on the previous state and control actions. But when it comes to a real system, we know that this is not really how the way it works, because we know that the state are not coming from evaluating the dynamics, but rather your system has its dynamics, and you get the states by either sensor measurements or state estimation. So in other words, this computational graph is broken when you're considering applying this conceptual computational graph to work with tuning for real system or physical systems where the data are not exactly coming from the computational graph. Okay, so how do we get the gradient to proceed? Well, we noticed that if you cannot do backward, then let's say you have a trustworthy model, or say a nominal model, where you believe that the model can confidently represent what your system is experiencing. That's only the zeroth order information. You can actually pull the first order information out of that system and use that to get the gradient. So to do so, we first observe this decomposition using the chain rule so that we can outsource the gradient of the loss function to theta by outsourcing it to the sensitivity of the state to theta and the control to theta. Okay, and then the question becomes, how do we get these two highlighted sensitivities? Well, the answer is simple from that point, because we can simply do differentiation to the both left-hand side and right-hand side of the dynamics. And then you can get this, first order equation that describes how the sensitivity states are being propagated with the data. So by data, what I mean here is whenever you get new state, new control actions sampled from your system, you can plug them in here into this coefficients and this coefficient, and this linear system can help you to propagate the sensitivities forward. And by the time that the horizon ends, you want to compute your loss, and at the same time, you can use this propagated sensitivities to compute the gradient. So this is a forward in time procedure. So you can do this in parallel to your system's evolution. In other words, you can choose to stop this procedure whenever you want and then update the parameter. Okay. So I hope this can give you an idea of how we do gradient computation for possibly data that come from a real system. And that's all for the first version of DiffTune. Okay, so there's still something we try to solve where that's not quite satisfactory here. Basically, we get the gradient, that's nice. But now the question is, when we look at the gradient descent that we use, we actually have to tune this alpha, that's the learning rate or the step size, when you're doing gradient descent. So in other words, there is hyperparameters that we need to tune for auto-tuning. And according to the students who work with me on this, they really hate to tune the hyperparameter. So we're asking ourselves, okay, can we eliminate this hyperparameter in the auto-tuning so that we can do hyperparameter-free auto-tune, or say true auto-tune? Okay, the answer is yes, but I want to show you how we do so. Remember on the previous slide, we have shown the sensitivity propagations where we can propagate what are the sensitivities of the states and control actions to the parameters. Well, those sensitivities can be used here to help us get the hyperparameter free tuning. So the basic idea is this. If we can predict what the future state will look like without even perturbing the parameters, with that, you can predict the trajectory, you can predict the loss, and then you can eliminate the hyperparameter because you can use that prediction to tell you what is the best choice for the hyperparameter. Okay, so to give you a visualized idea, so suppose you have this first trajectory in blue, and then suppose you want to perturb it by a little bit, the parameter by epsilon, and then without actually sending this theta plus epsilon, the new parameter to your system to obtain the state, you can already get the first order approximation using the sensitivity states. And furthermore, with this predicted trajectory using the sensitivity states as the first order approximation, we can actually approximate what will be the loss if you apply this parameter change. And that gives us a really convenient way to do hyperparameter free tuning, because all we can ask here is to say, okay, how do I pick the next parameter such that I can get maximized stepwise loss reduction between my current trial and the trial that I'm going to do next. So with that, we have come up with two.
Hello?
Yes.
Nah, I guess your mother probably put it. Did you put it away? So, Miss, is your mother home?
Sorry, Corey. Oh, okay. So, okay. That's fine. Any questions? Maybe I should stop at some point.
No, go ahead. I think he was just not muted. He was talking to others. Go ahead.
Okay. All right. No worries. Okay. So, hyperparameter free, we have two approaches. It's all up to you, like at which level you want to do the optimization. For example, on the left, we have optimization over a scalar, where we simply change the learning rate to optimize or to maximize this one-step loss reduction. Or if you say, okay, I'm going to do vector optimization, where we want to decide entirely this new parameter change, not just a scalar multiplying the gradients. So you can do the second way, which is the vector optimization. So we call these two methods line search and Gauss-Newton. And here, interestingly enough, is that when you have a quadratic loss function, what will happen is that, first of all, you can get explicit formula for alpha star or epsilon star corresponding to the optimized hyperparameter in these two cases. And in the second case, when we're doing the vector optimization, we came to realize that epsilon star has identical form to the Gauss-Newton method frequently used in the optimization. So we named the second method the Gauss-Newton. And by the way, the first method is called line search because we trust the gradient and we search for the step size of how far we should move along that direction. Okay. Now, to summarize, we have now hyperparameter-based and hyperparameter-free methods. So the hyperparameter-based are gradient descent, vanilla gradient descent, or you can add a momentum term, which is frequently used in machine learning to accelerate the gradient descent procedure. Going from hyperparameter-based to hyperparameter-free, first order method, we come up with a line search where we simply optimize the step size to maximize the stepwise loss reduction. And then hyperparameter-free, going from first order to second order, we have the Gauss-Newton. And we name it Gauss-Newton because the Gauss-Newton uses the approximated Hessian. So we categorize it into second order. And then for second order, we also have this hyperparameter-based method, which we add a damping term, mu I, such that you can always make sure that the Hessian is positive definite. Okay. We compare the methods in simulations, and now I'm going to show you how they perform, how they look like. So again, through this this presentation, I'm going to use the quadrature as an example. And in this case, to compare these several methods for gradient descent, we use two trajectories. One is a circular one that's on the left, and the other one is a 3D figure 8 trajectory. So the reason we picked these two are that they are representing totally different operating region of the quadrature, where the circular one is more steady and the 3D figure 8 is more agile and then has frequent change in the directions. So we use these two to represent two working conditions, and now here are the results. So let's look at it in the hyperparameter-based or hyperparameter-free category. So for hyperparameter-based, you can see this blue and red ones that are associated with the gradient descent with momentum. And another one is the Levenberg-Marquardt. That's the hyperparameter-based but second order. So they're basically doing the job, and pretty much we know that the actual performance depends on how you tune the hyperparameters. So it's not quite interesting. Now, the interesting is when you look at the hyperparameter-free methods, which are line search and Gauss-Newton. We first noticed that, okay, Gauss-Newton give you fantastic results. It gets the fastest loss reduction, minimum loss by the end. But when we look at the parameters tuned by Gauss-Newton, these values are too large. And in a sense, they're aggressive gains that practically we don't trust them for a control system. So instead, we look for the second best, which is the line search that can still give you a satisfactory performance. And we will check the parameters. It looks fine. Okay. So that covers what we have done so far on the simulation side. And next, I'm going to show you how DiffTune has been applied, how DiffTune has been tested on a real system. Again, that's going to be a quadrature. So in this case, we're dealing with nonlinear quadrature dynamics, precisely 18-dimensional. And for controller, we're using a geometric control. That's nonlinear controller, and it contains 12 control parameters. So this is a very hard problem because later I'm going to explain like what we observed through the experiments. But results-wise, we have tested DiffTune on 3 circular trajectories that have different speeds. So the speeds will represent different level of aggressiveness. And through all the speeds, we can see consistent loss reduction. And notably, when we're doing this 3 meter per second circular trajectory, which, by the way, is really aggressive in the lab, considering the size we have is not quite big. We have attained 3.5 times tracking error reduction within only 10 trials. So this is a very efficient method that can give you a huge improvement within relative few trials. And here, what we came to realize through these experiments was that this gradient-enabled tuning is very efficient because, like I said, if you trust your nominal model, then you should trust the first-order information. And that first-order information helps a lot for tuning. So what you see here from this animation is the evolution of these 12 parameters through this 10 trials for the 3 meter per second case. So what happens is that there is a nonlinear or say hard to describe tendency of the parameters that they do not tend to go in one direction. Because specifically, if you look at this angular velocity gains, there are two terms of the parameters, which indicates that along these trials, there are 2 points where the gradient changed the direction of evolution, because the local nonlinearity indicates that you have to change the direction, because otherwise, if you stick to the original direction, you won't get efficient performance improvement. And why this is hard for a person or a grad student to tune, the reason is that, first of all, the nonlinearity there is clear after we do these experiments. But secondly, let's do not forget about the dimension of the parameters. So in this case, we have 12. And for us, for human, when we perform trial and error, we do very efficiently with only 1 or at most 2 parameters for each trial. Because if we tweak too many parameters in each trial, when we get the new results or the new evolution, the new evaluation, it's hard to tell which change on the parameters give you that change. So it's hard to make the consequential decisions, and that overall makes hand tuning very hard. Okay. So this is a demonstration of what we did with the tuning for the 3 meter per second case. Like I mentioned, there are only total 10 trials, and we're selecting 4 of them to show you how the tracking error are iteratively reduced through this 10 iterations. And as you can see in the end, the quadrilateral tracks the circular trajectory pretty well. Next, we're also asking ourselves the question of what happens if you apply these parameters to the trajectory that you didn't train or didn't tune on. So this is a frequently asked question from machine learning, where they want to know something they trained with a certain data set, whether it can apply to a different, say, test data set. So here what we did is our tuning are conducted on the circular trajectory, and we're comparing it, we're trying to test its performance on this variance of figure 8 trajectory that has very distinctive flying profile or speed and acceleration profile. One thing we notice is that on these trajectories, this parameter that are tuned for the 3 meter per second case, for the aggressive one that I just showed you, generalize well. And T2 is second to that. So this leads us to a conclusion that when we're tuning for these parameters, even though we're using one trajectory to tune the parameters, but these parameters effectively characterize the dynamic properties of these tasks or these trajectories, such that the aggressiveness of the circular trajectory in this 3 meter per second case is actually carried over to this variance of figure 8 for fast flying and fast changing the dynamics. So here is an illustrative illustration of what happened with the tuning, and we're comparing to the hand tune, which, to be honest, is very competitive in this case, and we didn't know how the student get to do that. But we see that for DiffTune that are generated on the circular trajectory, they perform pretty well on this variance of the circular, the figure 8 trajectory. And lastly, one thing, probably you have the question when I'm talking about this, is basically DiffTune is based on the nominal model for the gradients. And we're claiming that, okay, we're dealing with real system data that has noise and uncertainties. So how do we get these two things to work? Well, our claim is that noise can be addressed by filtering or state estimation. That's something we come up for now, but we're looking deeper into how the noise and uncertainties are influencing this first order information when you're doing the sensitivity propagation, and trying to, based on that understanding, to come up with a deeper way or better way to deal with noise and uncertainties. For now, for noise, we're just doing filtering. And for the uncertainties, what we mean here is that in your dynamics, there will be unmodeled terms, like the disturbance or some unknown physical properties or values of the system that causes uncertainty. And our approach here to deal with that is to compensate for the uncertainties using, for example, the L1 adaptive control. And intuition here is that when you apply L1, where you apply this uncertainty compensation schemes, what it essentially does is to try to cancel out the uncertainties such that you can preserve the nominal dynamics which you use for the sensitivity propagation, and that will indirectly preserve the validity of the gradient. So here we're showing what happens when you have DiffTune with L1 adaptive control. And to make it convincing, or to understand what are the individual contributions for these two components, we're using the ablation study method from machine learning to individually twig on and off of DiffTune and L1 to see which part work and how much it work. So throughout these three trials, three experiments on different speed trajectories, we see that both DiffTune and L1 can help with the performance improvement for tracking, but they're coming with different mechanism. For DiffTune, we're doing iterative update of the parameters such that the parameters is getting more and more used to the task you're assigned to the controller to do. Versus for L1, the way to see this improvement in tracking is by actually compensating for the uncertainties such that the performance is less impacted and you can get better performance. But overall, we see through these three tables that the best performance is obtained when you apply both DiffTune and L1 at the same time. And here is a video demonstration of the ablation study for the 3 meter per second case, where you can see on the top row we're doing on-tune parameters, on the bottom row, the second row, we're doing DiffTune. The left column is associated with it L1 off, and the right column is L1 on. So consistent with what we see on the table in the previous slide, when you apply these two methods jointly, you get to have the best performance. Okay, so that's pretty much the end of my talk. So before I end, I would like to talk about the tool we're using. So we have open sourced the tools that we're using for DiffTune on GitHub. So what this tool will allow you to do, or what it does, is it allows the automatic generation of the partial derivatives that are used for the sensitivity propagation. So in other words, all you have to do here to use our tool is to plug in your dynamics, plug in your controller, and then you can simply click the run script, and then through certain iterations, you can see an improvement in the performance, and then you can take that new parameters to apply to your system. So to help you understand what we're doing, we provide one template that can fit your custom tuning application, and two examples, including the quadrature case we're doing here, to help you understand how our tools are used. And finally, because all we're asking is differentiable controllers, so that means new network controllers are also supported in our tool set. Okay, so a couple of things moving forward. Right now, we have some results in applying DiffTune to a model predictive control, which is optimization based, and it cannot be explicitly differentiable, but implicitly you can do so. And with the gradients that we're developing here on the right, this is an animation of an MPC, where you can see here for the control, there are even saturations, which we can handle with no problem in the DiffTune architecture. Other things we're also doing are system ID, which also apply when we want to apply this idea for DiffTune. And in my personal perspective, system ID is almost like the due problem of controller tuning in the practical sense. And then we're also interested looking into the controllers or dynamics that has non-differentiable points. For example, this MPC is one example where this control saturation is a perfect and frequently used non-differentiable case in controllers. And lastly, I've been talking about performance throughout this talk, but to be honest, performance is not the only thing we're looking for. We're also looking for robustness, and the robustness design can be enforced or can be achieved through this parametric way of tuning. But we have to do something over the training procedure such that when we get the final parameters, we can claim certain robustness. And we have some preliminary results on that, and we have used the verification tools to validate the robustness. So that's the end of my talk. My gratitude goes to the collaborators, advisors, and students who work with me on this. And finally, thanks to funding agencies to provide the kind support. So thank you.
Thank you, Sheng. This was great. And if there are quick questions, we take. If not, we'll let Aditya get started on talking about this distributional robustness, the type of control architectures we're working with. Sheng, you have a question?
Yes, thank you. Great talk. I wanted to go back to this point you were making about when the computational graph is broken because the state comes from a state estimator. And so if you have a model of the state estimator, would that be another way of solving the problem? And second part of that question is, if you are thinking about complicated state estimator models, which are potentially not differentiable. Okay.
So for the first question, I think if you have, definitely we have an estimation model, and if it's differentiable, you can do one small step to include that one. But still, this fundamental issue is that the sensor measurements is not part of the computational graph. So my way of thinking about this is that if you think in a simulation setting where everything is based on precise computations, then computational graph is the way to go. It is the clear and accurate way to describe the system. But the difficulty is when you have an actual system that you have this physics and sensors that are not precisely described using these equations or as in the way in simulations. And that was one challenge we're dealing with when we're in the beginning coming up with this computational graph, that we thought, okay, that's perfect. Let's apply it to physical systems. And then, like when we're trying to implement, we realize, okay, there is a problem. We couldn't really program that in PyTorch or TensorFlow. So we come up with sensitivity propagation to do the computation.
Thank you.
For this, so for the second question, I think it's for non-differentiable functions or dynamics, right? So, okay, so we're still looking into that, but honestly, there's not much to be done. The reason is that non-differentiability is not something we can deal with, although there are alternative ways to determine what would be a descending direction at the point of non-differentiability, like the subgradient, which is often used in convex optimization where you don't have a gradient at some certain non-differentiable points. So this is one alternative. But overall, I think non-differentiability is not a big problem in terms that when you have non-differentiability, it often happens at discrete points, which if you look at the measure of the set, the measure of those non-differentiable points has a measure 0, which means that in reality, the probability of hitting those points has probability 0. So so we're looking deeper into that direction to see how to incorporate more general dynamics that it possibly includes the non-differentiability. But thanks for the questions.
If no more questions, we can switch to Aditya to get an idea of this distributional robustness, which is work done using our other sources of funding, maybe NSF, AFORS, and so on, but it's very relevant to this context because these advanced air mobility vehicles operate in environments where this language becomes just important to analyze the performance of the controllers in terms of distribution shifts. So Aditya, just get started and try to be quick. With 20 minutes, you said it should be enough. So let's be optimal.
Can you see my screen?
Yes.
The full screen, right?
Mm-hmm.
Okay. Hello, everybody. So given the time, I'll try to a little bit rush through it. As Naira introduced, this is our ongoing work on distributionally robust adaptive control. And this follows in nicely from what Sheng was talking about considering how does the system performance translate from training to testing. When you do it over one data set, how does it generalize to the data set the system encounters in its real operation? So I'm going to talk about, for motivation, the data-driven control pipeline, which is fairly straightforward. You have a system, we collect data from it, or we're given data from it, we perform regression. So I'm talking about model-based, but this can go directly to the policy and can be done in the sim. And from the model, we learn a policy that is then applied to the system. Now the claim, and it's not a surprising claim, but this is a distribution-dependent pipeline. The reason is that the data has imprints from two sources. One source is obviously the system, but the other source is the data logging policy. So a combination of this produces this imprint on the training data. So the training data distribution has its own signature, which we call the training distribution. And this is just what the data comes with. So this is in learning. Whenever we learn, we produce guarantees over the distribution of the data that is available to us. So now what happens is that this training data then pervades through the whole pipeline, because the regression is performed using the training data, and then the regress model produces the control design. So it has this built-in signature on what we have designed. And to look at the design process a little bit more, we see where the training distribution pops in. So once we have the data, when we do the regression, we do, say, empirical risk minimization. We're fitting parameters of a model, say f hat theta here. So our expectation is minimized over this distribution, right? Because it is over this distribution, then our controller, for example, or some feedback policy, is designed to satisfy some control objectives, but the probability of it meeting its control objectives are obviously defined using over this training distribution. So whatever we are learning, it is learned to satisfy it over the training distribution. However, we always encounter a distribution shift. That is, when we put the system into the real world with our learned controllers, the true distribution gets shifted because of various reasons, like the controller has obviously changed from the data logging policy, which was a human or an expert, to now the optimized controller. Also, initial conditions are different, but those can be handled using generalization theory. The main ones, what we consider, are the distribution shift due to epistemic and aleatoric uncertainties. So the parts of the system that we could not learn because we didn't have enough data, or data of good quality. And part B, aleatoric, is just the inherent randomness of the system that we cannot learn, regardless of how much data is given. So now, because of this distribution shift, our controller guarantees, which were the controller that was learned to satisfy some guarantees over the training distribution are no longer valid, because our distribution is no longer the training distribution, but it is indeed the true distribution. So this obviously puts this is something very critical, especially when it comes to safety critical systems, and also to be predictable in how the system will perform in the real world once you train it in your simulator or given your data. So we have these epistemic and aleatoric uncertainties that shift the distribution from true to so that the true distribution is not the same as the training distribution. Now, what we want to do is we want to be robust to these uncertainties so that we can exactly quantify how much the true distribution has shifted away from the distribution on which our system was learned, on which our feedback policies were learned. Because if we can do this, if this is a guarantee, then we know that our true distribution always lie within this ball around the distribution that we have already seen. Okay, and hopefully we can mitigate it, so we can make this the ball size small, where we're seeing the true distribution. And if we can get this robustness certificate, which is this circle, this ball of distribution delta D train, this can be communicated to the upstream learner to tell it, like, to not learn only on a training distribution, but learn robustly around this training distribution within this set. And it is a guarantee that your actual distribution will never leave the set because of the controller. And these guarantees, they're agnostic to the training distribution. So any training distribution should have this ball snapped around it within which the true distribution should lie. So this is like a communication where your system operates robustly, so your upstream can also now learn and incorporate these robustness certificates. So why do we care about these certificates in the space of distributions? So as I said, the nominal controller always learns, or any learn controller is learned to satisfy conditions over an associated distribution. Our availability of the true distribution is usually difficult because it is expensive or usually unsafe to collect. And so we only have what we are given, or say collected in a simulator. But if we can produce these certificates instead of hoping to get all the data of all the good quality, if we can instead produce the certificate which is agnostic to the training distribution, then we can our learning step can be made robust to satisfy conditions within this set of distributions. And so that when the controller or any learned components are put into the actual system, the system will behave predictably and quantifiably. So this brings us to our work on this, which we call distributionally robust adaptive control. And the idea is that usually what we have, what I've said in the past few slides, that we have this learn controller from the training distribution, and this learn controller is blocked into the real system. Now, obviously, we get this distribution shift because of the training data to distribution mismatch. So what we want to do is add a control augmentation so that we get this robustness guarantees around any training distribution, which limits the system to operate within this set. If we have this, then of course, as I was saying, the upstream learning can be made distributionally robust. And this is the control augmentation, which we call the ARAC, which we want to design to produce these certificates of distributional robustness. And we are going to use L1 adaptive control for this, for certain very, very appealing reasons, as we'll see. Just a very big, quick history on L1. The main parts, why it is so appealing is because of its guaranteed uniform performance bounds and robustness margins. So if we think about the set of distributions that we need, if they're uniform in time, that is very useful for operating a system safely and predictably at any point in time. And this is what we want for our data-driven systems. Just a quick timeline of our development of L1. In 2020, we started on the safe learning and control work, which is now on continuing with the previous presentation also you saw. And so DRAC falls well within it, but we are increasing our abstractions to the space of distributions. What controllers can we design for just guarantees in the space of distributions? So a little bit more on the systems that we consider. So we consider these nonlinear Ito processes. So these are just nonlinear ODEs that are perturbed by a Brownian motion. And the Brownian motion is a Gauss-Markov process. So it is Markovian and it is a Gaussian process. And the good property is that it has stationary independent increments, which makes it a Levy process. So stationary independent increments is in discrete time, if you think about it, if you have a system that you haven't learned fully, every time you take a next step, you will end up somewhere else than where you were predicting. And this will be a mixture of a deterministic perturbation and a random perturbation. And so the random perturbation, it makes sense to assume it that at every point in time, it is coming from the same distribution. So this leads to this the desirable properties of Brownian motion in modeling of uncertain and learned systems. Another good property is that it is continuous in time almost surely. So our system, the state of the system can be represented as a continuous function of time. The only bad part is that it is nowhere differentiable. So x dot does not exist anymore, the time derivative. Therefore, we use these differentials as dx rather than x dot. But the good thing is that we have the whole world of stochastic calculus built just to handle the processes which are nowhere differentiable and integrating with respect to martingales. So as I said, one of the big motivations of using Brownian motion, actually a very big motivation, is that Skorokhod proved that if you have a process that is almost surely continuous and has independent increments, then it will be Gaussian. So that is where the role of Brownian motion comes in, because it satisfies all these processes. Now, later we'll work on Levy processes, not now, but Levy is the same as Brownian, except that it is continuous in probability and not almost surely continuous in time, which is for physical systems, almost sure continuity in time makes more sense. So as I said, it makes sense to model uncertain systems. So we now look at the individual parts of our dynamics of what we have and what we don't. So our drift, so this is the deterministic part of the STE. So if I only have this term, I will have a nonlinear ODE. And it has uncertainties in it, epistemic. So first of all, the known drift components of this is what we know. We design our baseline controllers based on that. So this is where the learner has learned this representation. So f of x is what the learner has learned. And then we have these uncertainties, which can appear both in matched and unmatched, and they have their standard assumptions that they are locally Lipschitz in X and linearly growing. Now, the thing that makes it now different from a standard deterministic system is this diffusion term that pops up. And we have a very interesting diffusion term because the known diffusion component is uniformly bounded. This is a consequence of the existing results in the literature, which use a purely robust approach. And if the diffusion is uniformly bounded, then they can show that the system solution is robust. However, to counter that, we choose these drift uncertainty, which we allow to grow. So it grows at a sublinear rate. So it can be a Holder continuous up to a exponent of 1/2. But what happens is, because this is linearly growing, purely robust approaches can no longer be applied, because the system solution and hence the associated distributions, they all keep on growing, and you have a divergence. Does not explode in finite time, but it keeps on increasing. So we have a divergence. Another important thing that we did is that we have this parameter var theta, which allows us to consider the case where our control channel is being multiplied by the Brownian motion itself. So it shows up as a noise, and depending on the strength of this noise parameter. But we were able to show that if our uncertainty h, which is just assumed to be locally Lipschitz, if it is twice weakly differentiable, so it is in the Sobolev space S2 locally, which means that its first weak derivative is locally Lipschitz. So the standard assumption on H is that its first derivative is weak derivative is Lipschitz. Now we have its second derivative is Lipschitz. If we can do that, and these functions are locally essentially bounded, which they will be because they're continuous, then we can produce stronger results with a control noise. And this also is an interesting observation, because when we, as on the last question that Sayan and Sheng were talking about in the last presentation, sometimes the dynamics of the system that you learn, they can be non-differentiable. For example, if you're using ReLU activation functions, they're not everywhere differentiable, but they're almost everywhere differentiable. So they're weakly differentiable. So if our uncertainties, for example, or the system is learned with ReLU neural networks, our approach is applicable as it stands. So that handles it is fine if the paths are not differentiable, but it needs almost everywhere differentiability, which ReLU, for example, the most popular one, satisfies. So now that we have the systems, then we define our our nominal system. So this is what we have learned, which is the same as the true system, but except the epistemic uncertainties. And to keep the realistic scenario, both of them are driven by independent Brownian motions, because even though we know the distributions of the Brownian motions, we do not know the sample parts of them. So in a real system, if you're doing a planning with the nominal system, you would imagine your Brownian motion that the real system will encounter will be independent. And this leads to some fundamental limitations that cannot be avoided. But it is an assumption that we have to need. You cannot violate this. And then we have these distributions, or also known as the state measures. So the our true distribution is math-calc-qt, and our nominal, the distribution that we expected to see during learning, is star. So the difference between these two is obviously the distribution shift that we want to minimize. And just to bring it back to our learning paradigm, so the true distribution, so the qt is basically the true distribution the system encounters, and q star t is what our learning was performed on. So our controller guarantees are all provided on q star t under the assumption the system sees q star instead of q. So with the systems defined, we'll quickly go over the goals. So if as I said, our nominals, our learn controller is designed on this nominal system, and we do not want to put it in the true system because of this distribution shift. So what we want to do is that to still, so that the guarantees of safety and predictability are not invalid, what we take is in the true system, we take the learn controller and add this feedback compensation that we want to design, which I said we'll be using L1. And just in the language of these mathematical models, we have that these our true system state follows a distribution that remains uniformly bounded around the nominal, the distribution on which our controllers and dynamics were trained. And if we have that, of course, these, as I said, robustness bounds can be used upstream for distributionally robust planning, control, and learning. As far as what we mean by the boundedness of the distributions, we talk in the sense of the Wasserstein metric, because it is a true metric on the space of measures on Borel on the Borel's sets of reals. And so it satisfies triangle inequality, the symmetric property. So it satisfies all the properties that metric does. So pictorially depicting our goals, what we want to do is that if we have our true distribution and the nominal distribution on the right, we want to design the controller so that this p, any order p, Wasserstein norm up to a certain order p, remains uniformly bounded by some constant rho in time for all time. This implies that our true distribution remains bounded in a rho ball around the ideal distribution, the nominal distribution, which is known as the ambiguity set. So it is a set of distributions around the nominal distribution within which our uncertain system, the true system in operating, will remain in for all time. So this is uniform in time. But if it is uniform in time, then we can extrude this ambiguity set, this ball of distributions in time. And what we get is that over any arbitrarily large and bounded time interval, we get this tube of distributions evolving in time, which we call now the ambiguity tube. And if you look at it, this is basically now it's a set. It's another Wasserstein. It's another ball, but it's in the space of path measures. That is probability distributions on the space of continuous functions mapping time to your state space. So basically, instead of looking at the system that you at some point in t, the system state maps it to Rn. Instead, you look at the whole time horizon 0 to t, and it maps into a continuous function taking 0 to e to Rn. The good thing about this is that these certificates, then the ones that we are proposing to produce, they can be used for planning, where instead of where the planning or the safe operation, where instead of generating the trajectories of the nominal system pointwise in time with the robustness certificates, you can directly sample the full trajectory and the full robust trajectories. And you are able to do that using the Girsanov change of measure theorem for the known system. So from Q star, you can go to the Wiener measure, sample that, and use this robustness ambiguity tube guarantee. So either one of them can be used. One implies the other. This is because of Kolmogorov's extension theorem. So both of these guarantees come to our aid here. So I'm running low on time. I'm quickly going to the controller structure. So we use a standard L1 adaptive controller structure. We have 3 paths: the state predictor, adaptation law, and low pass filter. This I can have in details in my next talk. But I wanted to point out that a predictor takes the input from the system state, and the system state is an Ito process. So our predictor is actually a system driven by colored noise. And this is very important because then we can start to talk about when our estimation models, like vision-based models, are deeply learned over some distribution, the training distribution of images. But we can see it has some dynamics associated to it. But because of the estimation noise, it is not directly perturbed by noise. It is perturbed by a system perturbed through noise, so which is known as colored noise. So in our analysis, we have been countering that also, and we've been able to go through it. So it opens up further exciting directions. So just for a very, very quick numerical simulations. So we are going to consider the angular rate dynamics of a quadrotor. We have epistemic and drift and uncertainties and drift and diffusion. And these causes our distributions to diverge. So you can see in the red boxes, these are the Wasserstein metric pointwise in time between the ideal distribution, which is green, and it goes away and hides because the true distribution explodes. So once we apply L1, these are the marginals because I have 3 states. So if you look here, our red ellipsoid, so these we ran Monte Carlo simulation with 600 trajectories, and the red denotes our true system, green is our nominal ideal system. And you can see that the Wasserstein metrics, they actually they remain bounded, and indeed they go down. So as you see at the start, my system is sitting over here, then it goes towards my ideal system and then remains close to it. These points that you are seeing, these are some sample paths. So some of the solutions sample from the distributions at this time. So what we are doing is we are not estimating the Wasserstein directly from the samples at this moment, but we are fitting Gaussians on them and then taking closed form solution Wasserstein between them too. However, more accurate will be a kernel density approximation, which you can see on the top here. These produce much more accurate estimates of the density functions. So we'll be extending our empirical Wasserstein computation to compare to a theoretical bounds using these. Another interesting thing is, as you can see, the distributions come pretty close to each other, but then they just stay there. They do not collapse on top of each other. Where in a deterministic system, if your control action is theoretically very strong, you expect to arbitrarily go close to your desired state, in this case our ideal distribution, but we cannot do so, and this is the fundamental limitation due to independence of the Brownian motions between the two. So the distributions can be brought together up to a point beyond which you cannot do anything, because the independence of the Brownian motion means the noises keep on perturbing the states, the sample paths around each other. And this is reflected in the theory as well. And similar, we get, these are just again the marginal ellipsoids for the same system. And we get the same, that we converge very well in the Wasserstein, but only up to a non-zero limit. And just my last slide. So this is still, the experimentation is very, very new. We are extending it to contraction systems. What the main goal is that we can do VNV of control systems which have these learned components in the loop, because we have now these distributional certificates. So we can make these learned dynamics and controllers robust, because we have a knowledge of this certificate which the controller is guaranteeing. And because of the color noise analysis, we also want to do the sensing, vision-based sensing, which will allow us to propagate these data-driven certificates throughout the whole perception, planning, control, and back pipeline. So we want to close the loop with these distributional robust certificates as a language pervading throughout the whole pipeline. And recently, we also started distribution robust planning using our controller with one of our collaborators in South Korea. And that is all. Thank you.
Thank you, Aditya, for this kind of wonderful presentation. So let's see if we have questions, because we are a little bit over time already. But, you know, with 12 co-PIs, each of us is getting one chance per year to present. So this was our chance after the 9 months of all other presentations. So we wanted to give an idea of the big picture of our lab, what's happening. There are a lot more other directions. Obviously, we work with Cheyenne on D&V using his verse library for verification, and we have other collaborations with Louis Shah and many others. But this is what maybe still not collaborated well enough within the ULI team. That's why we isolated this slice of work for today's presentation. So any questions, let us know. We can also meet offline. If you're all out of time, the recording will be uploaded within the few hours.
This is Louis. I just have a comment. You have a new student, Wu, right? Jing Wu, if I remember right, just joined the new NSF contract. So it turns out that the integrate with the model-based approach for optimization and the machine learning is centered, is a center theme about this new program. So I highly suggest that Sheng did a good work, and then the approach is similar to Yang.
So this is Yambi's project.
Yeah, so
Aditya,
probably they should talk, because they took a similar approach. And it's also the new NSF project.
It's Yambi's project, and Jim Wu is assigned to build.
That's exactly.
Work.
I just said people should talk because the approach is so parallel.
Okay.
Now,
Thanks, Louis.
Okay, I have a really minor question. So I heard that the Gaussian-Newton approach makes you uncomfortable because it's too large. The steps too large. You mean it doesn't converge to the right value for some reason, or it's just jumping around too much on the trajectory to converge?
Louis, so this is Sheng. I think the issue we see with Gauss-Newton is because the approximation of the Gaussian improperly scale the gradient or the parameter change. By the end of the several iterations, the parameters go very large. And in this case, we didn't enforce the projected gradient descent because we just want to see how this method work by themselves. Because otherwise, when you enforce the bounds, by the end, they look similar. So Gauss-Newton is very fast, efficient. It works fine in a numerical scheme. But for the subject of controller tuning, where we have some limitations on the parameters, we, for now, have some concerns on it.
Oh, I see. You think you would generate out-range data or something like that?
I'm sorry, Louis, I think I lost your
You
second.
mentioned that you want to constrain those parameter change within range based on the model. So is that what I heard is that sometimes you vary the bound imposed by the model? That's what make you uncomfortable.
Correct. Normally, that bound should be there during the projected gradient descent. But when we compare these different gradient descent methods, like the Gauss-Newton things, we turn it off.
Okay. Okay, thank you.
Sure. Thank you for your question.
More questions? So if we have no more questions, I guess maybe everyone is rushing to catch their next meeting. We can thank everyone for your attention and upload the presentation and the recording. Irene, are you good? So you wanted a detailed version of this presentation for our Friday meetings, which we skipped because we didn't have the slides ready. So now it's ready. We can maybe have a separate meeting sometime soon.
Yep. I forwarded, so I think we had some presence, Naira, from from some of the guys, so there might be some other follow-up questions, but this was very nicely done. And yeah, we can, see what the interest is and maybe deep dive into at least one or the other at future, actually probably both, but at the future presentations.
Yeah, sure, sure. I mean, each of these talks was worth a separate hour, but with
Yeah.
limited
Yes.
slots, once a month, we have to give all the co-PIs the opportunity to talk, and so we had to pack. Otherwise, taking
Absolutely.
two slots for us, leaving others with one slot is not fair. So, thank you.
Great.
So
Thank you, guys.
Right, thank you, everyone. So we'll upload and share the links, okay? If no more questions.
Thank you.
Bye. Bye.
Bye.